Assalamu alaikum students. Today we are designing the rotor, which is actually the last part of the induction machine, and then the induction machine design is then complete. The first thing whenever we are talking about the rotor design, as we all know, we have done the stator, the air gap, the stator slots. The number of rotor slots has also been decided, and at the end of today's lecture I will give you some bonus questions as well, 2-3 bonus questions which you can answer till your exam, maybe even the final exam also, and you can get absolute bonus marks, maybe 2 or 3 marks absolute, and that question will be open. We will talk about that at the later half of this lecture. Today, since we have the rotor design in front of us, so the first thing first over here that we have to first of all talk is this, that how we are going to actually move forward towards the rotor design. Now, we have already decided the number of rotor slots. So this is actually the rotor slots, or actually number of rotor slots, you can call it. Actually this is going to come here. So a number of rotor slots has been decided, and that number of rotor slots is actually the same as NB, which is the number of bars. Now why I'm using the word bars, because since this is a cage rotor, I'm talking about a squirrel cage machine at present. So this is a cage machine. So there are going to be bars over there, and then there is going to be an end ring. Now this does not mean that there is not going to be any laminations over there. Laminations are still there, and those laminations are going to be having those bars over there, and those bars are going to be filled with some molten aluminium, with some alloy being made over there, and we have talked about that in the previous initial discussion of induction machine. So when we have selected SR, because SR has a direct dealing with the number of stator slots, so SR is also selected. Now the next thing which we have to decide on this one is actually IB, and this IB is what? It is actually the rotor bar current. So IB, which is actually the rotor bar current, has to be actually decided also. Now certainly, as we all know, rotor bar current is going to be dependent upon how much power is actually going to come from the stator. Now just reminding you over here that induction machine actually works in the way that it is actually taking the flux from the stator. Some of that flux remains inside the air gap, so that it can actually evolve over there and remain over there for the Fleming's left hand rule for the mechanical motion being produced over there. The rest of it is going to be converted into an induced EMF inside the rotor. That is actually the bars over there, which are actually short circuited by the end rings over there. We will talk about that end ring current also just at the end of this lecture. So we are going to talk about these two currents, which are very important: the rotor bar current, the end ring currents over there. Now since I just told you that you have to assume it, that how the rotor, what power is going to actually be taken from the stator, and it's going to reach the rotor. Now since we are talking about something machines of like maybe from 1 horsepower to 10 horsepower, or maybe even bigger than that, maybe 50 horsepower or 100 horsepower over there, since this is a squirrel cage machine, and it's going to have not as such a fully dedicated 3-phase winding inside it over there. So a very simple equation which is normally used for this design is this, as an efficiency case, that the rotor MMF, which is actually going to be produced because of all that over there, this is actually going to be equal to the 85% of the stator MMF. So whatever MMF is being produced over there by the stator, assuming there is going to be certainly some leakage flux also there is going to be some flux remaining inside over there, then there is going to be some zigzag flux also being produced over there. So assuming it that 85% of it, it's going to reach the rotor over there, and that rotor MMF is actually going to be. Now what is stator MMF? We already know that, because what is MMF? We all know it's actually magnetomotive force. Now what is magnetomotive force in stator? This is going to be equal to, if I just put in very simple equation over there, this is actually going to be equal to, because it's a 3-phase machine, 3 multiplied by the stator current multiplied by the stator number of turns per phase. This is very important. This is either going to be TS or TPH. It's totally up to you, whatever you want to use. but again this is going to be per phase, so this is going to be the stator MMF. So this is going to be 0.85 into 3 into IS into TPH. Please remember, in stator MMF I have not taken the number of slots over there. I have taken, because each slot is going to be filled with a lot of number of turns of the stator winding over there. Now on this side over there, that is actually the rotor MMF over there. Since I know I am actually interested in the rotor bar current at present, so I'm going to use this IB over here. So this means that IB is going to be 1, because rotor MMF, magnetomotive force, and this is actually going to be multiplied by. Now here one thing very important, because I'm talking about a squirrel cage machine, a cage rotor at present, so there is actually no dedicated winding. It's just going to be a bar over there, and that bar is going to have a current flowing through it, right? That current is IB. So I cannot multiply IB by some number of turns. I can only multiply it by SR, which is actually the number of rotor slots. So now number of rotor slots multiplied by IB, but you have to divide this all by 2. Why? Because even if it's going to be a 2-pole machine or a 2-pole rotor in this case, so half of the slots in the rotor, they are going to be a cross, half of the slots there is going to be a dot. So practically it's going to be SR divided by 2 number of turns for the rotor over there. So I hope you understand this thing, that you have to multiply IB, which is actually the bar current, multiplied by SR divided by 2. And this IB again is actually the RMS current. This is very important. This is the RMS current, just like this IS was the stator current over there. Now, so this equation is there in front of you. Now this equation can be easily be solved for your IB. IB is going to be then equal to this 0.85, and here this will be 6 IS into TPH divided by SR. So this is a very simple equation. You already know SR because you have already decided on this one. TPH and IS, you have already decided it on based on your stator design, and then you have the 6 as a numerical value and 0.85 as the percentage which you have assumed. Now for very big machines, the very good machines, you can even increase this from 85, but induction machine, we all know that it's having an efficiency something in the range of 75 to 90 or 85. So 85 is still a very good value, I guess, a very good value. You can even take this at 0.80 or something like that. But again, this is dependent upon how much air gap. If your air gap is certainly large, then certainly this factor is going to be smaller. But 0.85 is actually the factor being used in your books as well. Now the next thing which is going to be is actually going to be the rotor bar area, which is actually the bars over there inside the cage. Now for those who have a little no idea over here what I'm actually talking about, if these are the end rings, let me just make this over here, and this is my end ring. And let me just draw it with some other color, the bars over here. This is the first bar supposedly, this is the second bar over here, this is third bar over here, this is the fourth bar over here, and certainly this is the sixth bar over there, and then certainly this is going to be, remember I'm not going to do any skewing showed over here. These same bars will be on all 360 degrees of the side, and when this whole rotor is going to be used over here, certainly this is going to be made up of some rotor shaft over there. So in short over here, this these orange color ones, these are the bars which we actually are designing at present, or we have found out the current, and this one is, these are the end rings over there. So we are actually trying to find out, now we have already found out the current in each bar, which is actually IB over here, or simply I actually small b, which is actually the same thing used in your book. So this is the cage rotor which we are designing. Okay, so these rotor bars are actually important. Now how these rotor bars have to be designed, this is very important. What should be the area of this rotor bars over there? This is going to be a very important factor over there. Now, if these bars are going to be of very big size, for example, if I have this rotor over here, let me just make a small rotor shape over there, and inside this one, supposedly I am going to make a small rotor bar over here, and this is circular in nature, like this, or maybe this is something having a shape like this one. We will talk about in detail just now that what is going to be the effect over here. or maybe this is something deep rectangular slots over here like this. Now each one of these rotor bars, so these are rotor, this is the rotor, and each one of these are the rotor slots, and in this rotor slot you are going to have the conductor melted. There's the aluminum conductor made of some alloy being added, maybe most probably silica is going to be added, and some alloy is going to be formed, and that is going to be filled inside this one. And then at the end you are going to put this purple color ring over here, and that ring is going to actually short all these conductors over there as shown over here in this diagram. Now screwing will also be done. That is actually a different aspect based on what harmonic you actually want to cancel. Now if before I go on towards these three different types of bar, there is also a fourth type of bar in which you don't have any opening, and this is just placed inside it over there, which means now the advantage of having an opening or having something like this, which is going to be called as a semi-enclosed or semi-enclosed slot. Semi-enclosed slot, there's actually going to be no advantage over here. Reason, because you are going to melt it and then you are going to put it inside. It's going to be just simple molten aluminium. So it's not going to be having semi winding. So you're not going to place some winding inside it and you are going to have it turned something like this, like stator. So this can be advantageous, and this type of slot is going to be called as a closed slot. Now one thing very important, if you are going to use semi-enclosed slot or closed slots, that's a totally different discussion. But before I go on towards the semi-enclosed and closed slot discussion, the area of that rotor bar, the area of the rotor bar is going to have a direct effect on the torque, and especially the starting torque of your machine. This is very important. So the area of the rotor bar is going to be having a direct effect on the torque over there. Now if you remember, I'm not going to go towards the formula and all that stuff you have done in your machines course, but the torque of your machine, that was highly dependent upon the rotor resistance R2. This R2, that equation, if you go on towards your Chapman, chapter number 5, I guess, over there, then this is the rotor resistance. This is going to be a direct relationship over there. Now for those who have a little bit ambiguity what I am talking about, let me just draw the torque slip curve over here. So if this is the torque, this is the slip over here, or maybe the speed over there, and from here the slip is from 1 to 0. So this is my 0-degree line over there. And if you have a rotor resistance on a smaller side, so what happens, the curve is something like this, and the machine operating region is maybe like something in this region, the shaded region over here. No problem. The speed is from the ns point to a very, very small, so the slip region is very, very small over here. But on the same hand, if you make a machine that is going to have a little higher value of rotor resistance, so what will happen, the starting torque is going to be high, and the same curve is going to be something like this. Now to achieve that value of torque over here, for example this one, so now the shaded portion is going to be something like this over here. So now what happened, the operating point of the same machine, which is having a R2 resistance larger as compared to this R2 resistance, you have made one advantage over here. You have got a very high starting torque. This is the starting torque of your machine. Here this is very, very small, and here this is very, very large. But the advantage is this, that despite having large starting torque, you are having the operating point in very large slip region, and because of that large slip region you are going to have more efficiency losses over there. So copper losses are going to be more, and this is completely true, because if rotor resistance is going to be on the higher side, you are going to have high value of copper losses over there. So very simply, if I just write it down over here in some words, so this means that if you have a high resistance or R2, this means that you let me just so you are going to have a good starting torque, but the copper losses are going to be on the higher side, and also the efficiency, because machine is not going to always work at the starting region. it's always going to work in the shaded region mostly, because that is actually the main operating point. So you are going to have, for high resistance, you have advantage in the starting, so you can lift a very heavy load from a very small machine also. But the disadvantage would be that here the region in which the machine is going to operate is going to be a high slip region. And for those who still don't remember it, the rotor copper losses, if you remember it, that was equal to S times PAG. What was PAG? AG was the air gap power that was actually flowing, and S was the slip of that machine. So if certainly S is large, the rotor copper losses are going to be large, and directly speaking, rotor copper losses are dependent upon the rotor resistance, so they are going to be on the higher side. On the other side, if you have a low value of R2, this means that you are going to have a poor starting torque, and you are going to have the copper losses on the lower side, and the efficiency is going to be on the higher side. So this is one aspect over there. So either you have to decide on one way or the other. Now, since I have told you previously also, machine design is actually a trade-off subject in which you have to decide either you go with that side or the other side. But if you want to reap the benefits of the both ways, then you have to do with something in the middle range. This means that the rotor resistance has to be selected in such a way so that you can actually get a little bit reasonable starting torque also, and the running of the machine is also not in the high slip region. So something you have to have a medium value or medium decision value over here, so this means that over here, if you are going to have a high value of the current density of the bars, this is very important. So if you are going to have the high value of the current density of the bars, so this means that you are going to have a low value of AB. What is AB over here? AB is the cross-sectional area of the bars over here. And so if you have a low value of AB, you are going to have a higher value of the rotor resistance over here. And let again explaining it, if you are going to select a large value of the current density in the bars, you are going to have a low value of the area of cross section in the bars. So you are going to have a larger low value of area means higher resistance, and this vice versa around. If you are going to go with a low value of the current density, you are going to have a high value of AB, and this means that you are going to have lower R2 over there. So actually the point of discussion is here is this, that by selection of the current density for the bars, you are going to actually decide that you want to keep the rotor resistance large or small. So based on this one, the the delta B, that is actually the bar current density, this value, the bar current density, this has to be kept from something 4 to 7 amperes per mm square. Now the book is telling us that approximately something a reasonable value of 5 to 6 can be selected, and that is actually a reasonable value for such sort of a cage machine. The range is very dynamic from 4 to 7, and certainly if you are going to keep it at 4, you are going to get a very good machine, because it's going to have a lower R2, the efficiency is going to be very good, but it's not going to have a very good starting torque. So it cannot lift very heavy loads, or even if it will try to, it will actually have a large value of current being taken, and the machine can actually damage itself. So if you want to lift a heavy load from smaller size machine, then certainly a high starting torque is going to be required. So when you have selected your current density, that is actually the bar current density, then you can actually find out the area of your bars, and then certainly that area is going to be equal to IB divided by delta B, and certainly this value is going to come in millimeter square. IB we already found out before by having that rotor MMF and stator MMF equal. So the area of the bars AB, this is actually the area of bar or one bar, that is actually going to be found out over here. This is the rotor cage rotor bar, which is actually being decided over here. Now when you have done the area of the bar, coming on to the next thing, which is very important, which I just left previously, is the shape of the rotor slot. Now shape of the rotor slot is a very important factor over here, because I just told you over here, I will just go back over here in this discussion when we are discussing about this two types of slots. One is semi-enclosed slots, the other one is going to be the closed slot. Now, very easily over here, if you have a closed slot, something like this over here, and if you are going with some maybe circular shape or one thing, but there is no opening over there. So what is going to happen? This is going to be used for maybe very a small machine. So if you have something, a machine of maybe like 1 horsepower, 2 horsepower, this is going to be very good. Why? The advantage would be that since there is no opening, okay, there is no opening, so the flux lines which they have to travel, because from the rotor, the current which is going to flow in this bars, it is actually going to interact with the field inside the air gap and then give rise to a Fleming's left hand rule. So this opening is actually going to be not there. So this means that you are going to have less reluctance over here being offered. So when you have less reluctance, so this means that you are going to have less magnetizing current also over there. So you are going to have less magnetizing current over there, or in short, by having those no openings over there, you are not having any losses over there. And since this is no opening over there, another advantage which you are going to have over there is this, that your operation is going to be smooth. It's going to be very quiet. So if there is an opening over there, and in this opening certainly there is going to be filled opening over there, but again that opening is going to have a little bit aberration with the sound air traveling over there, so it's going to be not a smooth over there. So per secondly there is going to be a zigzag flux, as I told you previously also, and since it's going to have less reluctance over there, and it has going to have a less magnetizing current, but the disadvantage is this, these are something of the very good things over there. But if you are using a closed slot, the disadvantage is this, that over here all it is covered with core, and when this is the lamination core over there, this means it's going to have more leakage flux, which means that the flux will not travel from the rotor bar towards the air gap. It will try to tend more inside the rotor. We don't want it. Just like in the stator, we wanted the flux to travel towards the rotor. Here also we want the flux to actually travel to the air gap. Air gap is actually the point from where you are actually going to develop that mechanical motion. So we want all the fluxes to be directed towards the air gap. So if the flux, it remains inside the core, it is having more leakage flux or more leakage reactance in the first place. So now when it's going to have more leakage reactance, what does it mean? If you remember the leakage reactance formula, or the equation for the rotor over there, we had over here two terms. One was Jx2 and one was R2. They were the rotor resistances. What was X2? This X2 was the leakage reactance. So when this leakage reactance is on the larger side, this means that you are going to have a less starting current. More value of Jx2 means, because what is going to happen in the start, you are going to have a slip equal to 1. Why 1? Because if you can all see over here, when the machine is starting from 0 speed, if I have the speed also plotted on this curve from here 0 to ns, that is actually the speed. So when the machine is starting from 0 speed, at that point slip is equal to 1. So when slip is equal to 1, you are going to have Jx2 on a very, very high side. So certainly when this is going to be R2, if you remember your equivalent circuit, this was R2 by S also, if you remember the equivalent circuit of an induction machine. So you are going to have less starting current. So when you have induction machines which are going to have a less starting current, you can start those machines very easily on DOL, which means direct online starting over there. You don't need any something Y or delta starter over there. But having more leakage reactance also means that you cannot have more overload capacity, which means you want to run your machine to a little bit more overloading. You want to actually take out more juice from that machine, so that it's not going to be possible. So a closed slot, you are not going to get more juice out of it. So it's only suitable for smaller machines. Now you may get the idea. In the very start I told you that this is more suited for the smaller machines over there. But if I move on towards the semi-enclosed slots, semi-enclosed slots, you have one opening over there. Now in this opening over there, they are more closer to the surface over there. So they are not going to have that smooth operation. Yes, there is going to be a trouble over there. Their reluctance is also going to be a change over there. Magnetizing currents are also going to be on the higher side. But yes, there is going to be less leakage flux because they are more closer to the surface of the air gap, or the air gap is closer over there. So leakage reactance is going to be on the smaller side. So in other words, they are going to have more overloading capacity in these machines which are having semi-enclosed slots. Now there is a one type of slot over here, as you can see over there. I have drawn this bar slot over there. This is actually a deep bar slots, and I hope you have an idea about this deep bar slots from your machine scores, that in this deep bar slots, the advantage it takes from both of these over here. If you see, when it's going to be covered with all aluminium inside it over there, and when the machine is going to start from rest, listen this carefully, when the machine is going to start from rest, the slip is going to be 1. So when slip is going to be 1, this is very important, when slip is going to be 1, the rotor frequency is going to be Fr into F into F1. What is F1? The stator applied frequency. Now in Pakistan we are applying a 50 Hertz. So what this means, that your rotor induced EMF frequency is going to be equal to 50 Hertz in the very start. So now the rotor is having 50 Hertz over there, and we all know for higher frequency the current always flows in the skin of the conductor. So for this particular conductor over here, which is actually a bar over here, the current will only remain in the upper area of this one. And when it will remain in the upper area, in the starting only, when it will remain in the starting, it will develop a more torque for the machine. Why more torque? Because when the current is still remaining inside this red color area over here, it is having less area, larger resistance is being offered. It's not flowing in the lower portion of the area. Yes, it will be there. I'm not saying it's totally going to be zero, but the major chunk, because the frequency is important over there, the frequency is 50 Hertz in the starting. So what is going to happen, you are going to have more current density over here. That rotor resistance is going to be large over there. So what is going to happen, you are going to get the advantage of the higher starting current. But when the machine has started, the slip comes down to back to its normal value. The rotor frequency then comes back to just like 3 or 4 Hertz or 5 Hertz at the maximum case when you are working in the normal working region. Then the whole deep bar is actually having all that current, and now you are actually having, so this means by having this deep bar, you can explore this one, you can Google it out also over there. So the deep bar rotor, the deep rotor bars, they can be actually used for the combining of these two curves over there. So you can actually take a very high starting current also, and you can take the advantage of this small working region for that torque also over there. So this is very, very important that your required torque is being met over there according to your demand. But again, yes, there is going to be some problem with this deep rotor bars over there as well. Leakage reactance for the lower range of this one is going to be more, so it's not going to give you the same overload capacity. So overload capacity is going to be more, well, if it's going to be a different type of slot. But overall, when you are going to use semi-enclosed slots, they are normally used for big machines over there. And if you are having a very small machine, since it's just going to be filled with some molten aluminium, so it's going to be a closed slot over there. Okay, now we are going to talk on the end ring currents. We have decided on the shape of the rotor bars or shape of the rotor slots over there. We have talked about the rotor bar current. We have talked about the rotor bar area, the current density inside it over there. So now the end ring current, or actually the rings which are actually going to short circuit the bar currents, is actually very important. And here the total current which is actually flowing inside the bars is actually going to meet up, and it's going to be short circuiting the whole thing. So if these end ring currents are not there, the end ring is not provided, the machine can actually practically not move in any way. So this end ring current is very, very important, and the current density of this end ring current has to be decided very carefully, again, because it's going to take on all the currents from all the bars, and then it's short circuiting it. So the entering current is going to be phase displaced also, and it's also going to have a different value also, because all the bars. Now I'm going to take the case of a very simple two-pole machine, and since if it's a two-pole machine, so this means that the stator is going to have two poles. So if it is a stator, the stator also has two poles. So the rotor also has two poles. So this means that I have only two pole pitches inside the machine. So which I mean by this, over there is two poles, north and south, over there inside the machine, which is the minimum one. Now the bar currents are going to be sinusoidally varying. Now we have talked about this very extensively, that there is going to be space harmonics, slot harmonics, and all that stuff. But if we take that into consideration for the bar currents, they are going to move, or they are going to vary RMS sinusoidally, or they are going to move or vary over there because of the square waves or whatever that are going to be formed over there in the space, then the discussion becomes very difficult. So I'm going to assume over there that the bar currents, they are having their magnitudes and directions change in the individual conductors over there, and they are changing from instant to instant over there, and it's changing sinusoidally. This is very important over here, that they are changing sinusoidally, and this sinusoidally will only be possible because according to Faraday's law, E is equal to N d phi by dt. So this means if the flux is changing sinusoidally, and what is the flux? Flux is actually the MMF that is actually produced from the stator, and if it is changing sinusoidally inside the space, not with respect to time but with respect to space, then certainly the rotor EMF is also going to change as sinusoidally. By sinusoidally I mean that all the bars inside it, they are going to have a different magnitude at the same instant over there. But what I mean by this over there, supposingly if I have this MMF wave plotted over here, supposingly this is the MMF wave, and over here this is the two pole pitches. By two pole pitches I mean that if this is the north pole and this is in front of the south pole. Now this is the MMF in space from 0 to from 0 this point to the whole 360 degrees mechanical. This is 360 degrees mechanical. So when I have this 0 to 360 degrees mechanical over there, so if I have this one over here, let me just make this a little diagram, and let me just use a little different color over here for let me just use this blue. Now over here in this MMF waveform, if I have this 0 to 360 degrees, the rotor bars are going to be there. Assuming that these rotor bars over here, they are going to be like 12 or 14. It's totally up to me how I actually want to name them over there. But assuming it that these are going to be rotor bars over here. So this is my first rotor bar. Then this is going to be my second rotor bar. This is going to be my third rotor bar. This is going to be my fourth rotor bar. This is going to be my fifth rotor bar. Or let's just assume it's just 5 over here. I'm not going to extend it more than that. And if I have this 5 more over here inside under the south pole, these are just rotor bars. This is very important. These are just rotor bars. Now these are 10 rotor bars, which means that my number of rotor slots over here is equal to 10. This is very important over here. Now based on this rotor bars, there is going to be an end ring, and that end ring is going to short all these conductors over here like this. I hope you are getting the idea. The whole rotor, which is actually circular in shape, is now opened on a piece of paper with all the bars shown in front of you, and dependent upon the MMF waveform which is produced over here from the north and the south pole, you are going to have an EMF induced inside the bars based on the value of that flux, which is changing sinusoidally through space. So what this means over here, that you are going to, corresponding to this bar, supposedly the first bar, you are going to have a very small value of over here. So I can call it a very small arrow over there. The next one is going to be a little more large. Why? Because the rate of change of that flux is over there. The flux value is different, and all the bars are moving with the same speed. This is very important over there. So at that particular instant when I'm observing this whole machine, so then next one, it's going to be a little bit more large over there because this is coinciding with the peak of that flux waveform, and then afterwards it's going to again come down, and then this is going to be very small. So this is going to be 5 arrows, and I have taken conventionally over here in front of the North Pole. These currents are, or the currents or EMF, actually you can take them as the currents or EMF, is totally up to you. So all these 5 bars are actually going to have a current flowing in the upward direction as shown over here, and the next bars, let me just draw it with some other color over here. Sorry. So in this one, it's going to be a little same, and it's going to be like this. So in front of the south, its direction is going to be opposite. So all of these 10 bars, which are actually the rotor slots, the magnitude of current is changing over there. It's changed at any instant of time. I have drawn these 10 bars over there, and these 10 bars are actually going to have some current flowing in each of them, and their magnitudes are completely different from each other, because I am assuming that the MMF waveform, which is going from 0 to 360 degrees mechanical, not electrical, this is very important. I am taking the whole machine over here. So 0 to 360 degrees, which means the whole circle. It is a 2-pole machine, so it's going to have one north pole and one south pole. And I am assuming that it has no harmonics involved over there. I'm just taking the fundamental over here. So it's just north and south pole, and the MMF waveform is changing sinusoidally. Now when this is changing sinusoidally, you are going to have this black color bars giving you the direction of current in the bars. The light blue color over here showing the direction of the current in these bars below. So this means that in front of these bars, the currents are decided. Now how you are going to find out the end ring currents? Because we have found out IP as an RMS value. Now here, since we have assumed it that these currents are actually going to be flowing inside the bars, the end ring currents are very, very important over here. Now if you see over here, before I proceed on towards the numerical equation over there, one thing has to be decided very importantly. This current over here, which is flowing over here, this is going to be flowing over here, and this is going to flow like this. This current is also going to flow towards here like this, and it's going to reach over here from here like this. This current, half of it is going over there, half of it is flowing over there, and it's going to flow like this. If I zoom it over there, let me just give you an idea what I'm talking about here again. So I have this current is flowing over here totally. This current is also going to flow towards the end ring over here. This current over here, half of it is going over here and half of it is going over there. So what this means, at this particular instant in time, the end ring currents at this point, let me call this junction as A, at this junction the end ring current is going to have the maximum value. Why? Because this bar and half of this bar, they are actually feeding the current at this point, because from this 2 bars and half of this bar, assuming the resistance is equally bifurcated in this whole thing, so 2.5 bars are putting the current at this point A over here. So this means the end rings are going to have the maximum current at point A, and if I take this point as B in the end ring, at point B, because half of the current is flowing over here towards A and half of the is flowing towards the other side, and certainly going to match up over here from this side, then at point B the value of current is 0. Now this is very important point. Listen to this very carefully. At point A, all the bars, which means this is bar number 1, bar number 2, and half of this bar, 2.5 bars are putting the current through this end ring. I am concerned with the end ring at present, current as present. So point A is going to have the currents from 2.5 bars, and at point B the current is still flowing. It's not like this, the current is not flowing, but at that particular point where that third bar of that north pole is actually there, at that point half of the current is being splitted, so point B is at 0 current. So if I take a particular position on the end ring, that point is having a zero current over there. Now what this means actually, now let me show you over here. If I want to now plot the end ring current, if I want to plot the end ring current, and this is my medium line over there, since point A was at the maximum current over there and point B was at the minimum current over there. So what this means actually, that I am going to have the end ring currents like this. It's still going to be sinusoidal, but end ring current is going to be displaced by 90 degrees. This is very important. The bar currents are flowing dependent upon the flux waveform, and based on that flux waveform you have that arrowhead shown over here. I've taken the case of a two-pole machine having only 10 bars. You can make this for 12 bars, 14 bars, whatever number of bars. Only the number of bars inside one pole is going to increase if you increase the number of rotor slots. But the end ring current is maximum at this point, and as shown over here. So at particular, remember all these diagrams I am drawing over here are for at any particular instant. As the machine will rotate in some time, all these bar currents are going to change and their orientation is going to change. Certainly in some systematic way, not abruptly. So the end ring current is physically displaced over here. Now if I draw the same bar over here, the bar current over there, the bar current was actually like this. The bar current over here, this is the IB and this is the IE. So I hope you are getting the idea that the bar currents and the end ring currents, they are 90 degree displaced from each other. So bar currents and end currents, they are 90 degree displaced from each other. Now how to find out this end current? This is very important. Now to find out the end current, if I see over here, I've seen this one over here. What I have done over here, the maximum current of the end ring is at point A, which is this point A. So the maximum value of IE is going to be from 1 bar, 2 bar and half of this bar. And generically speaking, this is approximately number of bars under half the pole pitch. What is pole pitch? Pole pitch is equal to this form. And what is number of pole pitch in terms of number of slots? That is over here in terms of 5, because the number of rotor bars are 10. So this means that under half of the pole pitch, how many number of bars you have? You have just like 2.5. So this means that the end ring current, let me just write it down now. The end ring current, the maximum value of the end ring current is going to be equal to the number of bars over half a pole pitch and multiply this by the average current per bar, because I don't know the value of current in the bar. I only know the RMS value of that IB. So this means if I want to find out the maximum value, I have to multiply the number of bars over half a pole pitch, multiply it by the average current per bar. And if I now write down in terms of equation, what is the number of bars? Number of bars over half a pole pitch. How many number of bars are there inside the machine? They are SR. And if I am going to talk about number of bars per pole pitch, that will be equal to SR divided by P. In this case, what was the number of bars? That was 10. But how many number of poles are there? There are 2. So this means SR divided by 2 is 5. But I want to have a value of 2.5, which is actually half of the pole pitch. This is half of the pole pitch. This is full pole pitch over there. So over here, SR divided by 2P is actually going to be the number of bars over half a pole pitch, and you are going to multiply this by the IB average current. Now how you are going to find out average current over here? Average current is certainly going to be found out by the maximum value multiplied by 2 by pi. I hope you have understood and got this formula before in your power electronics course. You know already IB RMS. You can find out your maximum value by having RMS multiplied by the under root 2, assuming again it's a sinusoidal. Assuming again it's a sinusoidal, which is again an assumption because harmonics cannot be totally lost over there. So your IE maximum is equal to this equation. Now in this equation you already know your SR, you already know your number of poles, you already know your IB RMS, but you don't know IB max. So let me just put in one value more over here. So IB RMS is equal to IB max divided by under root 2. We already know this, right? Because the maximum value divided by 1.414 for sinusoidally varying waveforms, we already know that you have to divide it by the peak value divided by 1.414, and that 1.414, and that already gives you the RMS value. So this means that the above equation can be changed to, this is IE maximum, can be changed to SR IB under root 2, that will actually change over there under root 2, and in the denominator I have pi p. So this means that IE max is equal to SR IB under root 2 divided by pi p, and since this is the maximum value and the end ring current is also the RMS, so IE RMS is equal to already IE max divided by under root 2. So this means that this equation and this equation, you use these two, and the final form is this, that if you want to find out IE RMS, this is going to be simply SR IB divided by pi p. I could have already written this equation from the very start, but I wanted to give you an understanding that the maximum current which is happening at the end ring current is actually going to be produced by number of half of the bars over a pole pitch multiplied by the average current per bar. That's why I took this one from the maximum value, and then using that maximum value and assuming it's a sinusoidal, I have now found out that the RMS value of the end current is equal to SR. IB is already known, that is RMS value. Again, this is RMS value divided by pi p over there. And now the last thing, which is very important, that you have to decide on the end ring current density. That is over here the end ring current density. So this delta E is going to be something from the range of 5 to 8 amperes per mm square. Now this is a little higher from the bar currents. Why? Because these are the end rings. So they are going to have more access to the airflow, so they can be cooled down a little bit easily. If you remember the previous one, they were having a range of 4 to 7. This one is having a range of 5 to 8, so that because they can be cooled down easily, they are on the outside end of the rings or the cage over there. So delta E can be changed from 5 to 8. It's totally up to you how you want to actually do it. And when you have selected your value of current density, you can find out AE, that is actually going to be equal to IE divided by delta E. So when you have found out AE, then from your AE you can easily find out your TE multiplied by TE. And what is TE in this case? This is the thickness of the end ring, and this is the depth of the end ring. So when you have got this, you have to select both of these values depending upon how your cage is actually being done over there. And when you have selected it, the whole rotor design is almost complete. This is the cage machine design, and today what we have done, we have found out the total squirrel cage machine design. Please kindly go through example number 8.6 of your book. This is very important as far as the, I'm talking about the R.K.Agarwal book. Please kindly go through them and in that example you have the end ring designed over there, and the number of rotor bars are given, and all that stuff has been given. The stator slots have been given, the rotor slots have been given, and the end ring currents are designed over there. So this is lecture number 8 over here, and hopefully in the next lecture I will just decide on the wound rotor, and hopefully this induction machine design will be complete from my side. Thank you.